Good afternoon, everyone. So we will continue with our lecture material, topic 7, last topic. But before that, just for the sake of the earlier class, just now, the earlier tutorial class, I didn't manage to find the time to go through the analysis of the solution, okay, which I went through with the second class, right? So the second class students, just bear with me for a bit. First class students, the students from the earlier class. So I just want to show you an analysis of the steady state solutions. By right, after you have solved the IVP that we have derived, so after you solve this together with the zero initial conditions, you are going to get the solutions given here. Okay? Of course, you solve by Duhamel's law because your E of t is making the system inhomogeneous, having some excitation. So, I mentioned before that after you solve, you got to do some parametric studies, right? Typically, what we'll do is that we'll plot out the functions in some graph plotter and then vary those parameters to see if the changes in your solution make sense according to the changes given to the parameters. So that's, of course, building up your experience, your intuition, right, as well as your analytical ability. There is another way to analyze the solution. That is by looking at the steady state values and see if they do make sense. So this problem actually gives us a chance to do that because if you look at the graph or if you were to look at the solution, right, you can observe that the steady state values of the currents I1 and I2 are 10 over 3 and 25 over 3 respectively, as shown in the red and blue curves here. So there is some steady state currents, can see from the image there. So how can you analyze the validity of the steady state values? Because if you look at the circuit, this one we already mentioned just now that the inductor responds to the changes in current, right? So which implies that if you were to have a steady current that is not changing, then the I prime is zero, what? Correct or not? I prime is zero. So if I prime is zero, then the inductors are short circuited effectively. That means inductor is just a coil of wire or just a continuous stretch of wire. So therefore, there is no resistance or there is negligible resistance. So if that is to be the case, that means you can easily convert the circuit here involving inductors into one that is only having resistors. Okay? So this is the equivalent circuit at steady state after a long time has passed, such that there is no longer any changes in currents. So therefore, if you were to just do a simple analysis, right, of the currents going through R1 and R2 respectively, you can see that R1 isn't so easy. This one is like 10 volts, right? So 10 volts is applied across R1 and R2. Okay, because this is effectively a circuit in parallel. Okay, that means the two resistors are in parallel with the battery source here. So therefore, you take 10 divided by 3, you're going to get the ampere, what? So that is the steady state ampere as you see here. Okay, because your transient circuit is going to approach the steady circuit as your current change go to zero. Okay, so I hope you can also get familiarized with such an analysis. Okay, a steady state analysis of your transient solutions. Can? So I take it as you are fine with that. So now we are going to continue with our topic 7, last topic. My aim is actually to finish today so that next week we only need to go through the tutorial questions. Okay, but I am skeptical because the last part quite a bit to go through. So therefore, we'll just go through at a comfortable pace. Okay, then we need to extend. Okay, so the story is next week is your last week of lesson. Then after that, right, the week after next, which is next Tuesday, is your finals ready. So which means that the consultation session online, or do you guys want a consultation session, or you think you don't need? Okay, so what's going to happen is this. By this Friday, I will upload the past year exam, past year finals. You must do, okay? I mean, you can don't do if you think you're that good. Okay? So, right? So, after you have tried the past year, then we have next Wednesday as our lesson, right? Of course, you can ask me on any of the tutorial question or the past year questions by then, but I'm not going to upload the solutions yet, okay, for the past year question, for the past year paper. So next Friday, there will be a consultation, okay? So next Friday, there will be a consultation online, right? Then after that, Tuesday is your finals ready, can? So that is the plan for Math 2, okay? Yeah, so because if I were to wait until Monday, I think it's a bit too late already, right? So I think we do it on Friday, consultation. Then you have Saturday, Sunday, and Monday, right, to revise through and prepare. Okay, as I mentioned to the earlier tutorial class just now, if you scored not bad for your CA, right, it shouldn't be that easy to fail the module. As long as you scored quite well for your CA, like B lah, okay, you should have no problems passing your Math 2. Unless you totally flunk and get single digit for your exams. Okay, quite difficult. You must put in a lot of effort to get a single digit out of 100 for your finals. Okay, because as I'm going through the tutorial questions, I also showed you how to get the low-hanging fruits, right? So get those low-hanging fruits first. Okay, then typically you should be able to pass if passing is your thing. Right? Of course, for some students, you want to get an A, right? So have to work hard, definitely. Yeah, so coming back to our second order linear ODE. So last lesson, we stopped at this part, right? Which is the modeling of the suspension system. Okay, so the suspension system, which is also called the harmonic oscillator model, right, is a very common model in all of engineering. Okay, because things vibrate. Why things vibrate? Because things got stiffness. Stiffness, right? So stiffness is the thing that causes something to vibrate. Okay, so like a building, there's stiffness. Like a bridge, there's stiffness. Like a cantilever, there's stiffness. Like your body, there's a stiffness. So therefore, as long as an object has stiffness, it's going to vibrate. And as long as it vibrates, then it can be modeled using the second order linear ODE. Okay, and that extends also to electronic and electrical systems. Okay, because there is also some kind of wave motion persistent in electronic and electrical systems. Okay, as you probably have gone through, and you will be going through more of those in later modules. Okay, so therefore this is an important model. So therefore we are going to look at it from the viewpoint of the suspension system, which is just like a suspension for a car, for example. So the suspension of a car, right, actually itself is very easy. I mean it's very straightforward. Okay, how straightforward it is, right? It's just comprised of a spring with a damper. So as I mentioned, you can have the spring, right? Because the spring is going to suspend the mass. But if you do not have the damper, then when the car chassis is being disturbed, such that when the car, for example, right, the wheel goes through a hump, okay, you might have this experience before, because some cars, right, their suspension system a bit soft, and the damping, right, the damper a bit too soft as well. So what happens is that when the car passes through the hump or some disturbance on the road, right, the car chassis that you are sitting in is going to vibrate up and down a lot. Okay, it's going to bob up and down a lot, right? So when that happens, well, it's not exactly very comfortable, especially if you bob up and down for a long time, because that's what makes you car sick. Okay, you'll get car sick. So therefore, you definitely need some damping. Okay, a damper. So therefore, the purpose of the damper is to, as the name implies, to damp out the vibrations. Okay, so you need to get the vibrations reduced to zero in the fastest way possible, typically in the fastest way possible, right? Without creating too much uncomfortable disturbance to your passengers. That is the purpose of a suspension. Okay? So if you were to model the suspension, okay, why we model the suspension is because after you have found out what is your mass of your car chassis, for example, including the passengers and everything, and you can choose the spring stiffness properly as well as the damping coefficient, that means the damper properly. Okay, and indeed, if you were to just Google for any spring catalog, a catalog that sells springs, like for example, car springs, you are going to see a few parameter values, right? You're going to see, for example, what is the overall length of the spring. You're going to see what is the diameter of the spring. You're also going to see the stiffness K of the spring. So therefore, when we design suspension systems, right, we have to choose an appropriate spring stiffness K. Because if you don't, then your spring can be too soft or your spring can be too hard. If the spring is too soft, then it might not be able to withstand the travel of the wheel. Have you guys experienced the car, right? When the car just ran past the hump. When the car ran past the hump, right, you may feel like the suspension, what we call bottom out. It means you hear like a pang. You might have experienced that because sometimes the driver, right, never see the hump and then just rush through. Okay, so that's called bottoming out. Bottoming out. Why bottoming out occurs? Because the force acting on the wheel is too large. Is that right? Okay. Or in other words, either the force is too large or the spring stiffness is too small. So you didn't choose a strong enough spring such that it can withstand the disturbance on the wheel. Okay, that's one consideration. And then the other consideration is your C, is your damping coefficient. So therefore, when you find dampers, right, you can find dampers online as well through the catalogs, right? One of the parameters that of interest will be the damping coefficient C. Okay, so these are very practical components, right? So we have to model them and form the solution. Then we can choose our K and C appropriately, dependent on what kind of response you want. Okay, because as you might have heard of, some cars, they want the ride to be softer and more comfortable. So typically, the damper, right, they choose kind of lower damping. But if you want more sporty feel, right, more sporty feel, the so-called feedback from the road, you want to be able to feel more pertaining to the driver, then typically the damper, they will choose a harder damping. Okay, so that the car does not so-called sway so much. So therefore, there is a lot of science going on with the spring and damper, and this is partly through the modeling of the suspension system. So after we have applied Newton's second law to model it, right? Originally, we have an excitation term that is mg. So that makes the ODE here inhomogeneous, and certainly we can solve inhomogeneous second order systems as you will see later on. But if possible, we try to make it homogeneous, because as what you have seen from tutorial 6, right, just now, homogeneous and inhomogeneous, the solution difficulty is not equivalent. When you use Duhamels, it's a lot more tedious. A lot more tedious. So therefore, if we can solve the homogeneous problem, we will prefer that. Okay, we will prefer that. So therefore, one way to make the system homogeneous is by taking the reference of vibration from the equilibrium state So this is something that we have gone through last week already. Okay, and that is right. Do not take reference from a state that the spring is uncompressed. Okay, take reference from the state y of t here, right? Whereby at this height of the mass, right? That means the spring has already been partially compressed due to the weight of the mass, due to the weight of the vehicular chassis, for example. Okay, so once you have that, your mg and kz term is going to cancel off exactly, because this is what happens, right, at steady state equilibrium. That means when the mass is suspended by the spring and there are no other forces acting. Okay, so when that happens, you will get a homogeneous second order ODE to solve, which will be much easier, as you will see in a bit. Okay, so now we are going to consider how to solve this second order ODE. The deal is we just convert to first order, because actually we don't know how to solve second order, third order, fourth order. All we know is first order. So we just convert all the second order and above into first order, and then we solve the first order ODE. Okay, so how clever is that? So basically we convert the problem that we don't know into something that we already know. So here comes the approach. It's called divide and conquer. Okay, now see, look at the second order ODE. But we can just let y prime, this prime term, be something else. So let's say, for example, v lah. So if, for example, y is displacement, right, y prime got to be velocity. Okay? So substitute that v into y prime. So v equals to y prime. So by prime must become bv. Can But if v equals to y prime, then it must be such that v prime equals to y prime prime. Just differentiate once more. So therefore, v prime equals to y prime prime, you can convert y prime prime into v prime. So once you have that, now you notice that, interestingly, I have a first order ODE in v. How come this is not we have a first order ODE in v. Correct or not? So we have v prime. There's no prime prime terms already. But we have a y term as well. So that means what I'm trying to say here is, right, v prime is dependent on v and y prime is dependent on v. Look at this. This is this what? The first equation. Then the second equation, this guy, is this. I just isolated v prime. Correct or not? I bring the cy across, become minus cy. I bring the bv across, becomes minus bv. But because there's an a that is associated with the v prime, so I need to divide it off in order to isolate v prime. So I just divide throughout by a. Can see that? So therefore, you have a coupled system. But we know coupled systems what? We solve them in topic 6. So therefore, rewrite this as a system in first order with the coefficients here for your matrix A. Okay, and your ft over A here obviously belongs to the excitation term. Is that alright? Can So if f of t equals to 0, then it's just a homogeneous first order system that we have solved already. Okay? So that's the divide and conquer approach. Any questions? So second order convert to first order system. And this idea, this approach extends readily to all higher order systems. If you have a third order, let's say py prime 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 plus qy prime prime plus ry prime plus sy equals to f of t. So you can see this is third order. Then what you do, right, is that let v be y prime. Let a be v prime, which is also y prime prime. So you just keep on letting variables be higher order derivatives such that you can convert the highest prime into one prime only. That is the approach. Okay? So therefore you can see from here, right? This guy if you isolate A prime, you are going to get the last equation. Then your V equals to Y prime is clearly the first equation. Your A equals to V prime is clearly the second equation. So then what do you have? A coupled system of three equations, three ODEs, and you can plug into a matrix form as well. Okay? So therefore, from here, you can see that second order you can convert, third order can convert, fourth order can convert, and so on and so forth. And therefore, eventually, it is just using Duhamel's. Any questions on the divide and conquer approach? So as I mentioned before, you will not be getting 3 by 3. Okay? At most, you get 2 by 2. So hopefully that gives you some confidence. So now it boils down to solving. So we return back to the 2 by 2. Okay? So firstly, we shall look at the homogeneous case whereby there's no excitation term. So therefore, the right-hand side will be 0, right? No f of t. So you can see that this is our matrix. Okay? Y prime equals to AY. So certainly, you will have your eigenvalues to be solved. Okay, so eigenvalues is solved from this thing called the auxiliary equation. Okay, so auxiliary equation actually very simple to obtain. So this one, you have to make sure you know. Okay, auxiliary equation. Hold on. This guy, auxiliary equation, is this guy. So how you get the auxiliary equation? Very simple. You don't even need to do the conversion. Okay, don't even need to do the conversion from second to first order system. What you will do is just look at the original ODE. This is the original ODE. So what you will do is to get auxiliary equation, just replace the y prime terms, y prime terms by lambda to the power of n. So that means if this is a double prime, right? 2 primes so n must be 2 So n must be 2, right? Then it must be lambda square. So you do notice that the number of primes is the exponent or the power, right, in the auxiliary equation. Okay? So the A, no change right? Just replace y prime prime become lambda to the square. Then by prime must be b lambda to the power 1. Then cy, because of no prime, so lambda to the power of 0 is just 1. So therefore, you only get c. So it is always like that. Is that right? So certainly, this equation will be exactly the same if you were to find the eigenvalues from the matrix A. But it's just that if you want to find eigenvalues for matrix A, right, you need to do some calculations. Obviously, this conversion will be more straightforward. Any questions? Can So I always try and give you the simpler approach. Can So now, eventually, what will be your y of t and v of t? Okay, I mean more concretely, you are trying to solve for the displacement function y of t. Okay, but along the way, you will also solve for v of t right? So it depends really on the type of eigenvalues. Okay, so let's look at, for the first case, if you get real and distinct eigenvalues, that is lambda 1 and lambda 2. Okay, what's going to happen is this. Now, you are just going to substitute lambda 1 and lambda 2 into the eigenvector equation. Okay, so this is your eigenvector equation where n can be 1 or 2, depends on what you substitute in, whether lambda 1 or lambda 2. Now, look at this. So, the original matrix, as you can see from here, this is a 0, this is minus b over a. So therefore, you minus lambda n, right, from the diagonals, which is what happened here. So obviously, you can solve from the second equation. Okay, but second equation more tedious. So therefore, what you do, right, just solve from the first equation will do. Okay, it will turn out to be the same. So therefore, if you solve from the first equation, you are going to get this expression. Minus lambda n times x plus 1 times y equals to 0, which is here. Then this goes to show you that your v, your eigenvector v, right, is just 1 lambda n. Okay? Because from here you can see what? Y equals to minus, or rather, y equals to lambda nx. This equation, right, gives you y equals to lambda nx. So therefore, you just choose x to be 1. You can get 1 lambda n for your eigenvector or for your eigenvectors. Can no problem there. So therefore, after you have found the eigenvectors 1 lambda 1 and 1 lambda 2, just sub inside. Can you see? Okay. Because A here will be diagonalizable, right? Because you have 2 eigenvalues, 2 eigenvectors. So therefore, A is diagonalizable. So we just use our general solution from topic 6. Can Let me write. This general solution is from topic 6. We just went through. Okay. So plug in V1, V2 generally in terms of lambda. And you can see that your diagonal matrix e to the dt will be e lambda 1t and e lambda 2t. Okay, diagonal. Then the c vector, as we have explained earlier on in the morning, we have c1 and c2 as the constant vector. Multiply out, you are going to get this solution. But what is it that you want? You want y of t. Okay, because originally you are solving the second order ODE for y of t, right? You look at the prime terms, is y. So therefore you're solving y of t. So this is your solution, the first row. Okay, so therefore your solution here gives you the general solution for a homogeneous second order ODE that has real and distinct eigenvalues. So everything I put in a blue box, you better copy down in your cheat sheet. Okay, blue boxes are the most important things in this module, as well as Math 3. Can blue box Is that right? Next, so we dealt with real and distinct eigenvalues. What about complex eigenvalues? Complex confirm distinct lah. Okay not? But it's not real it's complex So therefore, the complex eigenvalues always occur in conjugate pairs, alpha plus I beta. So what is the general solution? Actually, the general solution is the same as what we have here. It's the same. Okay, this guy is the same. However, lambda 1 and lambda 2, right? They are complex expressions, as you can see. So nothing much. We just sub in lambda 1 and lambda 2 as the complex expressions, and then just make use of Euler's formula to simplify. So this part, I will not go through the simplification in detail. You can check. Okay, just sub in, multiply out, then after that, factorize, and you are going to get the second blue box. The general solution will comprise of sine and cosine terms. So got meaning one, this one got physical meaning. Later on we will discuss. Okay. Now notice that the first expression is only exponential term. So no vibration. No vibration because you cannot vibrate without sinusoids, without sinusoidal terms. Exponential terms basically just decay, right, to 0 or go to infinity. Can Second solution, second blue box, for complex eigenvalues, you see some vibration. Okay, so let me write this down. Complex eigenvalues is going to give you vibration. So this guy describes vibrational motion. Okay, because you see the sine and cosine term inside the expression. Okay, and there's a exponential term. So as you'll see later on, this alpha, right, for suspension system is going to be negative. Alpha is going to be a negative real number. So therefore, there's a decay term, which makes sense because the vibration is going to decay with time because of your damper. So later on, we will see that. Lastly, as you might expect, we have real and repeated eigenvalues. Okay? So we're going to derive in tutorial 7, right, as part of an exercise. It's not difficult. because we just make use of the Jordan decomposition and we are able to get this expression. So notice that for real and repeated eigenvalues, the motion has also no vibration. Okay, there's no sinusoidal terms here. It's just t and e to the lambda t term. So therefore, there is no vibration, but there can be some a single bounce, you call it. Okay, later on we will look at what that means. So 3 blue boxes. You better have the 3 blue boxes inside your cheat sheet. Okay, dependent on the type of eigenvalues, you will choose the correct one to apply. If you choose the wrong one, it's a disaster. 10 marks, maybe you get 1 mark. If you choose the wrong blue box, let's say eigenvalue is supposed to be complex, you go and choose this one. Then 10 marks will get 9 marks deducted because you don't even choose the correct solution, dependent on the type of eigenvalues that you have. So how does the eigenvalues change? They change according to your parameters A, B, and C. Okay? So therefore, A, B, and C here will control your type of eigenvalues. Understand? So not to worry, we'll have some examples coming up. Okay? But make sure you choose the correct blue box, please. So now here's an example. How to use the correct blue box in writing down the solution. As long as you choose the correct blue box, right, actually the answer almost like give away to you. So we have a suspension system here. Okay, that is taking reference from the static equilibrium position. So solve the displacement response. So very simple. Already taking reference from static equilibrium. Wait, let me see. Taking reference from static equilibrium position. So therefore, what's the ODE? ODE will be my prime prime plus cy prime plus ky equals to 0 because there are no external forces acting on the mass. But then because mass K and C are given what? So therefore you just sub in. So we have y prime prime plus y prime plus 9y equals to 0. Okay, because we are just substituting in the values, the parameter values given. So now we write down the auxiliary equation. So auxiliary equation is, so you can see the y prime prime here is just lambda square. Y prime is just lambda. 9y is just plus 9. Can just replace the number of primes by the power. Okay? Then if you look at this, right, you notice that this guy is going to give us, well, can we factorize? Oh, no. We cannot factorize. So what do? We use the root equation, right? Or you can just punch your calculator, okay, to find the roots. So therefore, to find lambda, so lambda 1, 2 is equals to minus b, minus b plus minus b square minus 4ac over 2a. Okay, or rather, in this case, right? Okay, never mind. I just straight away plug in the values. So minus 1 plus minus root, because your b is 1 here. So it'll be 1 minus 4 times a is 1, c is 9, over 2 times 1. So just use the root equation, or you can punch your calculator. So this guy is going to be what? Minus half. Minus half plus minus. So what is this? This is 1 minus 36. 1 minus 36. So that is a minus 35. Root minus 35. Root minus 35. Divide by 2. Agree or not? Agree, because you root a negative term. So therefore, the root minus 1 can be factorized out. So it'll be minus half plus minus I, right? Then if you take root 35 divided by 2, you're going to get approximately 3. You can check. If you take root 35, okay? You see you get 5.91, but you must divide by 2. So you get 2.96. Okay, 2.96. Of course, you can put 2.96, right? But I'll say that approximately is 3. So therefore, we have half plus, or rather minus half plus minus 3i. Approximately, yeah? Any objections? So, eigenvalues are complex. Complex. Okay, so for complex eigenvalues, choose the second blue box. Not difficult, I hope. Just choose the correct blue box. This guy is obviously complex. Okay, so where is alpha? Alpha is minus half. What's beta? 3. Any objections? No objections? Then you just need to write down the solution. So therefore, general solution is y of t equals to e to the minus t over 2, minus half t. Then multiply by d1 cosine 3t plus d2 sine 3t. So this is your general solution. And you probably know what comes next. Because you need to solve for d1 and d2 if initial conditions are given, and they are. Okay, your initial conditions have been given. You see? Y naught equals to 0, y prime naught equals to 1. So apply initial conditions. Okay? So you will apply the y naught one first. Y at t equals to 0. So that will be giving you e to the 0. Then you only have d1. Because this is d1 times 1, right? Plus d2 times 0. Because sine 0 is 0, right? So therefore, you're going to get d1. Okay? d1 times 1, d1, then times e naught, e to the power of 0 is 0. E to the power of 0 is 1. So you get d1, and that will be equivalent to 0. So there is no d1. So if there is no d1, that means the solution simplifies to only one term. Y of t equals to e to the minus t over 2 times d2 sine 3t. Okay? So this is the reason why you must apply y naught first. If you apply y naught and it simplifies, the general solution simplifies, right? You are going to have an easier time getting y prime. If you go and get y prime here, you can. But you're going to have a harder time because you have more terms. Okay, so it makes sense to apply the initial condition first for y naught before getting y prime. So from here, you need to obtain y prime because you need to apply the initial velocity. So from here, your d2 can be factorized out and you're going to have minus half. So use your product rule. So minus half e to the minus t over 2 times sine 3t, then plus e to the minus t over 2, 3 cosine 3t. Hold on, let me get some space here. Okay. So now you apply the initial velocity, y prime naught. So y prime naught, right, as you can see, you have your e to the minus t over 2. Okay. So therefore, you're going to get d2 times minus half times 1, because e to the 0 is 1. Then sine 3t is 0. Sine 0 is 0 plus 3 times 1 times cosine 0 will be 1. So this will give you what? 3d2. So 3d2 must be what? 1. Okay? So therefore, you have an initial velocity of 1. So hence d2 will be 1/3. So there you have it. Your particular solution. Your particular solution would be 1/3 e to the minus t over 2 times sine 3t. So that's the particular solution that we are looking for. Any objections? So you can see that after you found the eigenvalues, much of the work is just solving for constants. This type of question is like giveaway. Because just solve one quadratic root, then you use the correct blue box. Then after that, sub in the initial condition to get the constants. So hopefully you score the mark. Any objections? Very good. Okay, no objections. Let's look at the next example. So basically, same kind of problem, but now the damping increase. Okay, damper now becomes stronger, right? So harder to move the piston in the damper. You can see C increased to 6. Now if C increased to 6, right, the other parameter values remain unchanged. So which means to say that the ODE changes to Y prime prime, because mass is still the same one. Mass is still 1. Okay, so this is still 1. Then your K is 9, but the C is now 6. So therefore, you just have a 6Y prime plus 9Y equals to 0. So once again, the auxiliary equation. So you get lambda square plus 6 lambda plus 9. So which will give you lambda plus 3 whole thing square. So therefore, you can see that you're going to get repeated lambda equals to minus 3. Okay? So this is lambda 1, 2 equals to minus 3. So this is repeated what? Repeated eigenvalue. So repeated eigenvalue, you should choose the last blue box to apply. This is the one. You see? So that's how easy this is. So therefore, the solution is just e to the minus 3t, because your lambda is minus 3. Then you get c1 plus c2t. So now you apply initial conditions. So y naught equals to 1 e to the 0. E to the 0 times c1 plus c2 times 0. So obviously you just get c1 equals to 0. Okay, so c1 equals to 0. That means your y of t will be just c2t e minus 3t. So just differentiate, get y prime. We just repeat the procedure that we have done previously, but for a different solution function. So you get c2, right? Use your product rule. E to the minus 3t minus 3t e minus 3t. Okay? So now apply initial velocity. So c2 plus multiply by 1 minus 3 times 0 times 1. Okay? So therefore you just c2. But c2 equals to 1. Because the initial velocity is 1. And that's it. So therefore your solution is te minus 3t. Because your c2 is 1. Particular solution. Any questions? I hope this is easy enough. So then similarly, if you increase the damping further from 6 to 10 Newton second per meter, then of course you can solve, right, and get the particular solution here. Okay, so this one I won't go through in detail. Basically, it's the same procedure as what we have demonstrated for the past two examples. So the particular solution is this. Okay, more importantly, I want to analyze the three solutions with you. Okay, because actually the system is exactly the same, right? But it's just that you increase the damper. That means you increase the damping coefficient C and you get very different solution forms. Initially, when the damping is small, like 1 Newton second per meter, okay, 1 Newton second per meter, you get vibrations because you see that you have a sine 3t term, right? You are going to get vibrations. So if you plot out, you are going to see this green curve. Okay, so you see the vibratory motion. But if you were to increase the damping coefficient to 6, so much so that you get repeated eigenvalues, then certainly your Te minus 3t, right, is not going to get any vibrations because no sinusoids, right? No sine and cosine terms. So therefore, you get the orange color curve or yellow color curve. Okay? But then if you were to increase the damping coefficient further to 10 Newton second per meter, then as we have seen in the last slide, we get exponential decaying terms. Okay? So that is going to be, if plotted out, shown by the blue curve. Okay? So what is the deal with the various values of damping here? When you have low damping such that C square less than 4 mK, you are going to get sinusoidal terms, which means vibration. Why is it C square less than 4 mk because your auxiliary equation generally, auxiliary equation is m lambda square plus c lambda plus k equals to 0. Agree or not? Because it's always mck ma. This is coming from your ODE. My prime prime plus cy prime plus ky equals to 0, right? So the auxiliary equation generally must be m lambda square plus c lambda plus k equals to 0. So isn't this a second order quadratic equation? Right, second degree quadratic equation. So what's lambda? Lambda 1, 2 is minus c plus minus root b square minus 4ac now becomes c square minus 4mk, then over 2m. Okay? So the type of roots you get depend on the discriminant in the root expression. C square minus 4mk what? This guy is the critical term. Okay? So therefore, if you get c square less than 4mk, what do you have? C square less than 4mk. This is a negative term. If this is negative, you get complex roots already. Agree or not? Oh, sorry. It should be in green. Let me follow the color of the graph. Agree, right? This c square minus 4mk, if c square is less than 4mk, then this is a negative term. Negative means you get complex eigenvalues. Okay? Then what happens if you get c square equals to 4mk? Then this expression is going to be 0. Correct or not? So what's the root? The repeated root is minus c over 2m. So repeated lambdas. And finally, if your c square is more than 4mk, then this is a real number, what? I mean, as in this is a positive number. So you root a positive number, you get a real and distinct roots. Agree, Yes? No. As in, as long as you have c square less than 4mk, you're going to get complex eigenvalues, which is inevitably going to give you sine and cosine terms, sine and or cosine terms inside your solution. So that means as long as you have vibratory motion, we say that this system is underdamped. Is that all right? Okay, so what are examples of underdamped systems? Almost all vehicular suspensions. Almost all vehicular suspensions are underdamped. For comfort, you get a little bit of vibration, but not a lot. But you will still feel the vibration. Okay? You still like bob up and down maybe 2 or 3 times before going to some stationary motion or more or less stationary motion. Okay? But the extent of vibration you feel will not be that huge or else you get severely underdamped. Okay? Severely underdamped, as I mentioned, you get car sick. Okay? So then if, let's say you increase the damping such that c square equals to 4mk, then you're going to get what we call the critically damped system. Now in this case, the critically damped system here, right, repeated eigenvalues, you will notice that this is a type of vibratory motion that doesn't exhibit any vibration, but will go back to the equilibrium position in the shortest time possible. So this critically damped system is typically desired if you want the object to return to the equilibrium state ASAP. So let me write, return to equilibrium in shortest time. Okay, then I have to give you some examples. Okay, underdamped system. This one is most car suspensions. Most vehicle suspensions. Today, when you take the bus or take the car, or if you drive, you can consciously feel the vibration as you go through the hump. Then you will notice that actually you do feel a few oscillations, right? You bob up and down a few times before you remain steady. Okay, so that's for underdamped. Most vehicle suspensions are underdamped. Now, what is a critically damped system? that guy. If it is tuned properly, this one, if it's tuned properly, right, it will close in the fastest way. Okay, desired. So typically they will have to tune this. The damper is here. Okay, they tune it such that, right, it will close in the fastest way possible without vibration. Can correct lah. You give it like a initial displacement. So this one is like initial displacement. Initial displacement, let go. Then it's going to return to the equilibrium state in the shortest time possible, as fast as possible. Okay? So therefore, these are used for typically door mechanisms. So let me give some examples here. Makes sense because you don't want the aircon to, you don't want the hot air to rush in, right? So typically you want it to close fast, okay? But of course, there could be a case if the door, when it closes too fast, it becomes a bit dangerous, in fact. Okay, because the speed can be quite fast. Depends on the strength of the spring. So therefore, it is also okay if we have an over-damped system. Over-damped system, if you look at the response, right, is such that, right, it closes very slowly. You see? It goes back to the equilibrium in a longer amount of time. You see the blue curve? It doesn't like go back so fast. It go back slowly. So what is the purpose of such a system? When you have, for example, right, when you open the van, let's say there's a van door. Typically, you have to look at a van door. Okay? When you open the van door, the fella like, psst. Correct not? You don't want that to open too fast, because if it's open too fast, you'll hit your chin, Correct not? So you want like that. So that is a over-damped system. Because speed is dangerous. Okay? So over-damped system, right? So slow motion, desired, typically for safety. Okay? So example will be van door. Or rather the back door of the van. Okay, so you can see the different types of damping for different applications. So therefore, dependent on the object or the application that you are trying to apply such a spring damper system for, right, you will want to choose different amounts of damping carefully. Any questions? Very good. Okay, so of course, why I go through this thing is because if you get a question explaining the solution that you have in the previous portion, you have to think about that from this perspective. Okay? So now we are going to look at forcing excitations applied on the suspension system. Maybe it's a good time to take a short break before we move on to the inhomogeneous case because the solution is quite horrendous. So let's take a break. So let's continue at 3:15. Okay. So we are going to derive the ODE for a system that is subjected to excitation. So actually we do not have to include mg in our force body diagram, FBD. So in your free body diagram, as you can observe on the screen, do not add mg. Do not add the weight because the weight has been cancelled off by the compression of the spring KZSS already. So this one, do not add mg term. If they ask you to take reference from static equilibrium, cancel off already. So therefore, this is the free body diagram involving the three forces only. And if you take the sum of forces equals to my prime prime, the sum of forces is going to give you F of t minus ky minus cy prime equals to my prime prime. So therefore, your ODE is really ny prime prime plus cy prime plus ky equals to f of t. Okay? So that's the ODE. Simple. Now we are going to look at how we handle that f of t. So since it is a linear ODE with excitation, our good friend is Duhamel. Can I? Okay, let's ask our good friend. Okay? So now, assume that you have your initial condition given at t naught equals to 0. And then initial displacement is y naught. Initial velocity is y prime naught. Okay? We straight away apply Duhamel's principle. Okay? Because we already know the homogeneous solution already. Right? See? All our homogeneous solution has been derived. Okay? We have 3 blue boxes if you recall, right? So, homogeneous solution for repeated eigenvalue. Homogeneous solution for complex eigenvalues. Homogeneous solution for real and distinct. So we have all the homogeneous solution already, what? Can So we just extend to the particular integral and that will give us Duhamel's principle. So which is what is going to happen here. Okay? So basically what we do is we just put the f of t or f of tau inside the initial condition. Then, of course, that begs the question, you want to put it into the initial displacement or initial velocity. Last time, we don't have a choice. We only have one initial condition. Okay, so it's very obvious that you just put the f of tau d tau inside that single initial condition. But now you have two, so you have to think about which one should you put it in. So now, we will have to put the f tau d tau into the y prime term, into the y prime term. Okay? And why is it that this is f of tau over m? Because when you isolate y prime, when you isolate y prime prime, you are going to have f of t over m. Hold on. I better make it very clear here. So from here, this guy, so if you isolate y prime prime, then you're going to have plus c over m y prime plus k over m y equals to f of t over m. Can right? But what is f of t over m? Is an acceleration. Force. F of t is a force, what? Cannot. Force divided by mass. This guy. Force divided by mass equals to acceleration. Can? So, what is f of tau over m times d tau? Acceleration times time. This guy is acceleration. D tau is time. Acceleration times time is velocity. Can? So therefore, it makes sense to put the f of tau over m term at the initial velocity. Is that right? So this is actually just a repeat of what we did for the first order IVP. Okay, first order is just without the prime prime term. Okay, so now you have your prime prime term ready, but you have two initial condition. Right? Then Duhamel say that, hey, you just make it homogeneous. So remove the f of t term, which is what happened here. Okay, that's why it's called homogenized lah. Right? Then after that, the f of t or f of tau over m d tau just put at the appropriate initial condition. And we work out the initial condition to be acceleration times time. So therefore, it has to be at the velocity. Can? Okay? So you see the similarity for the second order ODE with the first order ODE. Okay, so originally you're trying to solve for first order last time, right? And then the homogenized IVP is just remove the f of t. Then after that, put the f of tau d tau at the initial condition. The same thing occurs here. Any questions with the Duhamel's approach? Very good. So If you're okay with this, then we already know how to solve what? Isn't this just now homogeneous equation we can solve? Then given the initial condition, the initial displacement and the initial velocity, can solve already what? So dependent on the type of eigenvalues, real and distinct, this is our solution. Okay, just few slides back, we derive it already. Apply the initial condition at t equals to tau. At t equals to tau, y tau equals to 0. Wait, I better copy down. Okay, y tau equals to 0. First initial condition, plug in. Second initial condition, y prime tau equals to f tau over m d tau. Plug in. Cannot. Okay, so you look at the two equations, it may look difficult to solve, but it's not. Okay, because you can always just take the second equation, take the first equation times lambda 1 minus the second equation. That will remove your first term. Okay, so the solution I won't go through in detail, right? R2, for example, R1 times lambda 1 minus R2 and all that. Okay, if you solve, you're just going to get C1 and C2 giving you the terms here. Okay, then you sub C1 and C2 into the general solution to get your particular solution. This is our particular solution. Okay, but this is what? This is just for one instance of the excitation, what? Correct or not? One instance. But you have many instances of your excitation. So therefore, you need to integrate. Okay, integrate respect to what? Of course, integrate respect to tau, which is what we have been doing all this while. Okay, so you can look at the expression. The 1 over m lambda 1 minus lambda 2 got no tau inside, so might as well just factorize it out. Then only the f tau term and the exponential terms with tau, right? You need to remain inside the integral. Okay, so therefore, this is our particular integral for real and distinct eigenvalues. The total solution is when you add up to the homogeneous solution. Okay, homogeneous solution plus particular integral, you will get the Duhamel's principle. Any questions? So another 3 blue boxes for Duhamel's for inhomogeneous ODE with excitations. Another 3 blue boxes. Just now got 3 already, right? So now for excitation, excited systems, right? You have to have another 3. Okay, from Duhamel's principle. So real and distinct eigenvalues with this added term. Okay. Next, how about if your eigenvalues are complex? No big deal. Sub the complex eigenvalue into the general solution and you will get this. Okay, so this one we discussed earlier on already, right? We get our sinusoids. Now you apply the initial condition. So once again, you have your initial conditions given here. Initial conditions. So you observe that the first initial condition give you this guy. Second initial condition give you this guy. Can right? So if you painstakingly solve, you are going to get D1 and D2 giving you this expression. Okay? D1 and D2 giving you this expression, the constants. Sub back and you will get this expression for your particular solution. Okay, you can see that the derivation is quite a hassle because you involve the compound angle formula. Okay, but no big deal. After we simplify, we get this. Once again, this is one instance of the excitation because just f tau d tau. What? Then what about the rest of the excitation function? You have to integrate. Okay, so once again, second blue box. Homogeneous solution with particular integral in this form if you have complex eigenvalues. Is that right? Can Okay, so altogether, you have gone through 5 blue boxes already. So I give you one last one, which is real and repeated eigenvalues. Okay, so since we didn't kind of go through the derivation process, we just went through the slides like it was nothing. So in tutorial 7, we will be going through the derivation process for Duhamels in detail. Okay, so I hope that you can try to derive on your own as well. So Duhamels, for real and repeated, you will get to this expression. So you see homogeneous solution plus the particular integral. Is that all right? 3 blue boxes. So altogether, this topic will have 6 blue boxes. Homogeneous 3, inhomogeneous another 3. Okay? If you are smart, right, you will just put the Duhamel's principle, the 3 associated with the Duhamel's principle. Why? Because for homogeneous system, you just cancel off this term, what? No need to put 2 lah. Cannot. Because Duhamel's principle comprise of homogeneous and the excitation term, cannot. So let's say you don't have excitation. F tau is 0, F tau is 0, then this whole integral is 0. So therefore, this will be the homogeneous solution. Isn't that legit? So in reality, you only have 3 blue boxes. Questions? Okay. So then there's a green box here. So it's called the essence of the Duhamel's principle. So this one I repeat like, I don't know, like 10 times already. So the essence of the Duhamels is it can be used to solve all inhomogeneous linear ODEs of any order, including PDEs that you will learn in Math 3. Okay? So as long as your solution to the homogeneous problem can be evaluated, then you can also write down the particular integral. Okay? Like what we have done for the 3 types of eigenvalues. So now we are going to go through this example and probably call it a day. Okay. What do we have? M equals to 1, K equals to 9, C equals to 6. Initial conditions are given similar to earlier examples. So now we are supposed to compare YH, YP, and Y of T. Are they logical? Can Okay, so you can see the F of T is 2E minus 3T, right? So this is something that we have derived before already. Okay? So from, I'm not going to re-derive lah. Can Should I re-derive? Okay, I think I better go through from scratch because I scared you blur. M y prime prime plus C y prime plus K y equals to F of T. Okay, equals to 2E minus 3T lah. Straight away put lah. Okay? Okay, wait. I put F of T first. So therefore, sub in the values. Y prime prime plus 6y prime plus 9y. So your F of T over M is F of T divided by 1. So this is e to the 2e minus 3t. Can right? So this guy is F of T over M. Never mind, I just put F of T. Okay. So now get the auxiliary equation first. We have done it before, but let me just repeat because you need to be able to do this from step 1. Auxiliary equation always put to 0. Okay, because you are considering the homogeneous case. This is just for getting the correct form because correct form of the solution depends on the type of eigenvalues. So therefore, this is lambda plus 3 square. So therefore, you get your lambda as repeated. Okay? So because it's repeated, you use the Duhamels for repeated. Is that right? Okay, use the Duhamels for repeated. So if you look at the initial conditions, same as previous. So no need to resolve already. YH, straight away write down. So from slide, okay, let's refer to the earlier slide where we solved this one. Slide 15. Okay, so from slide 15, the homogeneous solution, just write down. YH of T is TE minus 3T. Okay? Now, what about YP? Perform the integration. So, YP of T, 1 over M is 1 over 1. Integrate 0 to T. Then T minus tau, e to the lambda, but lambda is minus 3. T minus tau. Then f of tau is what? 2e minus 3 tau. Okay, nothing much. I just substituted the 2e minus 3t, replace the t by tau because it's f of tau, and plug it in. This guy. But this guy is chicken feed. Why? Because e to the minus 3t, then you got 1 plus 3 tau. This one minus 3 tau. So therefore, it reduces to the 2 can factorize out. Then e to the minus 3t got nothing to do with tau. Integrate 0 to t. T minus tau. D tau. Isn't this chicken feed? So therefore, your solution is clear. 2e minus 3t times t tau minus tau square over 2. Put in the limits. So your final solution will be 2e minus 3t multiplied by, so this is t square minus t square over 2. Then minus 0. You sub in 0, right? It's going to be 0 for both terms. So you can see that the solution is simply t square over 2 times this 2e minus 3t. So clearly it will give you t square times e to the minus 3t. That's your particular integral. Cannot. Then remember to write the final solution. Y of t equals to, just write this down, you'll get the mark. YH of t plus YP of t. So you're going to get TE minus 3t plus t square e minus 3t. That's it. This is your solution. Any objections? Okay, good. So now we just look at the 3 solutions that we get from homogeneous, particular, and total. Okay, so let's look at decimals. So your YH of t, okay, so that's equivalent to TE to the minus 3t. Can So let's restrict the domain to more than 0. So this is your YH. So let's put down YP. So it's a t square. Okay. So let me change the colors because I'll use blue for homogeneous. Then I'll use red for particular. Okay, then finally our total solution, y of t, right, will be YH plus YP then. So let's look at the 3 solutions. So is this legit or not? Is this legit? Firstly, the homogeneous solution is due to what? Due to initial condition what? Correct not? YH of t is a result of the response of the suspension system due to initial conditions. So what's the initial condition? The initial condition is such that there is no initial displacement. Isn't that correct? Okay? So let me write. This guy is entirely due to initial velocity. There is no initial displacement. So the initial velocity is 1 meters per second. And 0 initial displacement. Okay? So therefore, you can see that these expressions, this expression must bounce out from 0 because you have 0 initial displacement. And the initial velocity of 1 meters per second, right, is actually the slope. If you compute the slope here, right, it will be 1 meters per second. Okay? So therefore, it bounces up. And notice that because your system is critically damped. So critically damped means, right, it doesn't exhibit any vibrational motion, meaning to say there is no sinusoidals. So therefore, it will go back to the equilibrium in the fastest way possible. Okay? So therefore, this is due to initial conditions, response to initial conditions. Okay, in agreement with our understanding. Then the second one is the response due to what? Due to the excitation. Due to the excitation. So this guy, the red one, response due to excitation or external force. But what is the external force? The external force is 2e minus 3t, right? So 2e minus 3t is a force that will reduce to 0. Initially is 2 newtons. But 2e minus 3t will reduce to 0 slowly with time. Agree, Okay. So you see what happens. Because at time t equals to 0, you apply this force, right? So it's going to add on to the response of the initial conditions. Okay? This y of t is going to compress, but it's going to compress due to two factors. One is the initial velocity, right? So due to the initial velocity, your y of t is going to increase. But due to f of t, your y of t is also going to increase. So therefore, you see this part. Okay? If without initial condition, right, this is your response to the external force, the red curve. So therefore, you notice that this external force is maxed out at 2 and then reduces gradually with time to 0. So when your force here, external force here, reduce to 0, certainly it comes to a point whereby your mass must go back to the equilibrium because the force becomes 0 already, ma. So therefore, this must return to equilibrium. Okay, so returns to equilibrium as force diminishes. Make sense? If your force is not diminishing, it's a constant, for example, or it approaches some constant value, right? Then you will not see this. You will not see it returning. Okay, it will continue to go to some non-zero displacement. Is that right? So you can see that the net response, the total response, must be the sum of the two responses. Okay, so this guy will be the total response. So eventually, because the initial velocity is going to diminish, the effect of the initial velocity is going to diminish. Okay, and then your external force also goes to 0. So therefore, the total response must go back to the equilibrium state. Any questions or objections with the analysis? Good. I hope you can imagine the physical meaning of the mathematical expressions here. So I'm going to stop here for today and we will continue to finish topic 7 during probably the morning of next week. Okay? Then after that, we will finish up the tutorial 7. Let's mark attendance.